Hello students, welcome to GATE Academy Global. So GATE 2020 Electrical Engineering, we have one question from the EMT, and that question is, let AR cap, A phi cap and AZ cap be the unit vector along the R phi and Z direction. In the cylindrical coordinate system, the electric flux density is given as vector D is equal to 15 AR cap plus 2R A phi cap minus 3R Z AZ cap coulomb per meter square. The total flux in coulomb emanating from the volume enclosed by the solid cylinder of radius 3 and height 5 meter oriented along the z-axis with its base at origin. We are having the four option, which is 54 pi, 90 pi, 108 pi, and option D is 180 pi. So we have to calculate the total flux, and the total flux passing through the volume, and the volume can be called as the closed surface. So let's draw the diagram for the given question, because it is given that it is placed along the z-axis. So this is the cylinder which is placed along the z-axis with its base at origin. So the figure will be like this, and this is the y-axis and this would be the x-axis. So it is given that the radius of this cylinder is 3 and the height is 5. So we can say that here the z is 5 because it is starting from the 0, because its base is at 0. So we can say that it is z equal to 0 to 5. The total height is 5. Now we want to calculate the flux. The definition of the flux is phi is equal to integration d dot ds, flux passing through any surface. But here we have to calculate the flux passing through this solid cylinder, that is the closed surface. It is having the three surfaces, that is the top surface, bottom surface and the curved surface, and all the three surfaces when we combine it becomes a closed surface. So we have to calculate the flux passing through any closed surface. So it would be the closed surface integration. This is the closed surface integration of d dot ds. Now we can calculate the ds, differential surface, and we can also break into this form, like this is the top surface plus curved surface plus bottom surface. So this closed surface can be divided into these three closed surface, three surface, and this is equal to d dot ds. And another way to solve this question is if you apply the divergence theorem. So from divergence theorem, integration over the closed surface d dot ds can be written as integration over the volume divergence of this vector d dv. So this may be the shortest way to solve this question, because the divergence of d is very easy to calculate. Here we have to calculate the differential surface. If you apply this, so you have to calculate the direction of the surface, and according to that you have to take the dot product, and then when you integrate you will get the correct answer. We will see that solution also. So this is divergence of d. Let's find by the first method. If I apply this right hand side, so this is the divergence of d, and this would be 1 upon r del r, r into dr, plus 1 upon r del d phi divided by del phi, and del d z divided by del z. Now we are having the r component, coefficient of r component is 15. So this is the 15r plus 1 upon r square, coefficient of phi. Coefficient of phi from the question it is 2r. So this is 2r, and coefficient of z is minus 3rz. So we are having minus 3rz. So after solving this we get 15 by r, okay, and it is 0, and after solving this we get minus 3r. So it is 15 by r minus 3r. So divergence of d is 15 by r minus 3r, and we have to take the volume integration to calculate the flux passing through the closed surface. So this flux is triple integration, because this is a volume integration, and divergence of d is 15 by r minus 3r, and it is r dr d phi dz, and the limit of r is from 0 to 3. To make the cylinder, phi should be 0 to 2 pi, and height is starting from the 0 to 5. So when we multiply this r, we get integration r equal to 0 to 3. This is 15 minus 3r square dr, and phi equal to 0 to 2 pi d phi, and z equal to 0 to 5 dz. So if I integrate with respect to r, I get 15r minus 3r cube divided by 3, limit from 0 to 3, and this is phi, limit from 0 to 2 pi, and z 0 to 5. So this 3 and 3 will get cancelled. When we substitute this 3, we get 45 minus 27, and this is 2 pi, and this is 5 minus 0, which is 5. So 5 into 2 is 10 pi, and 45 minus 27 is 18. So the answer is 180 pi. So the correct answer would be option D. Now this is the one method to solve if you calculate the divergence of d dv, and if I want to solve using this method, if I want to calculate the d dot ds for the different surface, then what should be the approach? Okay, so let's try to solve this by the second method. Okay, now for the top surface, this differential surface is, see, this is the top surface, and in this top surface the z is constant, z is 5. So in this top surface the direction of the surface is plus az, which is in the upward direction from inside to outside. So this will be r dr d phi az. Hence we get integration d dot ds over the top surface is d is here we are having az, and that is az. So if we take the dot product, we get minus 3rz multiplied with r dr d phi, and this is over the top surface. So it would be double integration, and minus 3r square z dr d phi. So the limit of r would be from 0 to 3, and the limit of phi is from 0 to 2 pi, and the value of z here is fixed, which is 5. So the value is 5 into minus 3. The integration with respect to r is r cube by 3, limit from 0 to 3, and this is phi 0 to 2 pi. Okay, so this 3 and 3 will get cancelled, and we get 3 to the power 3, which is 27, and 27, and this will be 2 pi and 5. So that is 10 pi. Okay, so we are having 270 pi with minus sign. Okay, so this would be the value of the integration over the top surface. Next is for the bottom surface. For bottom surface, the differential surface will be, it is nothing but, this is the direction of the bottom surface. Okay, so this is the ds, and the direction of the differential surface for the bottom surface is minus az, because the direction of the differential surface is normal to the surface and also from the inside to outside. So if you go upward direction, that means you are going inside the volume, but we have to move from inside to outside. So this is inside and we are moving in the outside, that means in the negative direction, that is the minus az, and that is the perpendicular direction. So the differential surface is minus r dr d phi and az. This direction az is minus, that's why here it is minus sign. So now we have to solve for the bottom surface. So this bottom surface d dot ds is, we know that d dot ds, if the direction of the surface is az, then it is minus 3r square. So we can write minus 3r square z dr d phi, and this is the surface integration, so you can write this as double integration. Here the limit of r is from 0 to 3 and the value of phi is from 0 to 2 pi, and this is for the bottom surface, and remember that the bottom surface is lying at z equal to 0. So the bottom surface is lying at z equal to 0. For this integration the z equal to 5 was there because it was the top surface, but it is the bottom surface, so this is z equal to 0 here. So when for the z equal to 0 we substitute, this value of this integration would be 0. Without any integration we can directly say, because the z is constant here which is 0, so this integration will be 0. Now we have to calculate for the curved surface. So for the curved surface the differential surface will be the curved surface, that means we are talking about this part of the cylinder where the radius is constant, because in the cylinder on the surface the only thing which will remain constant is the radius. So the direction of this curved surface will be in the direction of r, which is constant. So in the direction of r the differential surface in cylindrical coordinate system is r d phi dz. Now if we calculate integration over the curved surface d dot ds, then it is double integration. This is the AR, and if I take the dot product with the R component, we are having only the coefficient which is 15. You can see this D in the direction of R is it is having the coefficient 15 only. So if you take the dot product D dot ds, then it would be 15r d phi dz. So here the radius is constant which is 3. The value of z is varying from 0 to 5 and phi is varying from 0 to 2 pi. So if I solve this integration, I get 15, r is constant which is 3, and this is 2 pi and this is 5. So 15 into 3 is 45 and 5 into 2 is 10, that means we are having the 450 pi. So this is the integration along the curved surface. Now we are having all the values. So about the top surface we are having minus 270 pi, about the curved surface we are having 450 pi, and about the bottom surface we are having value 0. So if you solve this you will get 180 pi, which was expected, because we know that from the integration over the volume divergence of d dv was 180 pi, and which is the correct option D. And if you solve with this formula, integration over the closed surface d dot ds, then also you will get 180 pi. The method is, there are two methods, the choice will be yours.